Hi guys, my name's Sarah Honeck and I'm a member of the Society for Radiological Protection, and today I'd like to share with you a really simple experiment that you can do at home based on one of our school's lessons plans available on our website to demonstrate the half-life of radioactive nuclides using Skittles. So the first thing that you need to know is that radioactive substances are unstable and therefore disintegrate or decay to become non-radioactive over time. The rate that this happens depends on the isotope of the element that we have. For some it can be thousands of years, like carbon-14, or it can be as short as a few seconds. So first we start with our cup of radioactive Skittle atoms. The first thing to do is count how many radioactive atoms we have, so go ahead and count them. Remember not to eat any of them yet, as they're all radioactive. So you can see that we've got 43, and we can put this number into our table at t=0, and you'll see as we go along that we start to build up a graph of the half-life over time. So now what we need to do is put all the radioactive Skittles back into the cup, give them a shake for about 5 seconds, which is the half-life of our Skittle atoms, and pour them back out onto the table again to represent the passing of one half-life. Now, any Skittles that land S up are considered to have decayed, so remove them and they can now be eaten as they're safe. So we started with 43, and the probability to decay is 50-50. So how many Skittle atoms would we expect to have decayed in this passing of one half-life? Well, it's around half, isn't it? So around 21 or 22. Let's see how many we end up with. So you can see that we now have 25 active Skittle atoms left, so not far off our estimate. The reason it's not exactly half is because radioactive decay is a probability, so we can estimate the numbers that will decay, but we can't say exactly. So again, we need to put the Skittles back into the cup, shake them for another 5 seconds and pour them out to represent a second half-life. Again, remove the decayed Skittles and record the number of active Skittles remaining in the table. So after that second half-life, let's see how many we have. We've got 19 active Skittles remaining, which is quite far off the estimated half, but as I said, don't worry, this is exactly the nature of radioactive decay, it's a probability. So again, we're going to go through the third half-life and remove any decayed Skittles. At the end of that third half-life, we've got 11 active Skittles remaining, and you can see our graph is starting to take shape. So we'll go ahead and complete our fourth half-life now, and we've got 6 remaining. Here's our fifth half-life. And at the end of that, we've got 4 remaining. So you can now see that our graph is starting to tail off, and you can see that there's a nice exponential curve forming. So here's our 6th half-life, and we're left with 2 radioactive Skittles. And after our 7th half-life, we're down to 1. Half-life 8, and there's still 1 left. Don't worry, as we said, radioactive decay is a probability, so it can't be exactly predicted, and we just need to make a best guess. So here we are, 9, still 1, and then here we are. After 10 half-lives, we get down to 0. So now you can clearly see the shape of the graph. It's a really nice exponential decay curve of Skittles. We started off with 43, and each time approximately half of the Skittles decayed. We never knew exactly when each individual Skittle would decay, but if we had a large enough sample, then we could predict how many would decay over time. And this is a really nice analogy for the nature of radioactive decay, where we can't see one individual atom decaying, just like we can't see one individual Skittle decaying, but we can predict it, and that it should be around half. So in radioactive nuclei, this rate of radioactive decay is described by the term half-life, and half-life refers to the time required for half of the nuclei in a sample of radioactive isotope to decay. Thanks for watching. Goodbye.